Welcome. In this podcast, we're going to study something called similar triangles. This relates back to our previous study of ratio proportion, as ratio proportion plays a dominant role in studying similar triangles. Now, similar triangles are triangles which have the same shape. So if you look at the two triangles in the first drawing, I've indicated with hatch marks that the angles in those triangles are equal. For instance, when I put a single hatch mark in this angle and a single hatch mark in this angle, this means no matter what I actually drew, I meant to draw them equal. Similarly here, the double hatch angle would be equal to any other double hatch angle in a nearby drawing, and the triple hatch angle here in the big angle would be equal to the triple hatch angle here. Now, we do that because it's impossible to really draw them the same. So we indicate what our intention was with our drawing. Now, in the drawing, you can see that when two triangles are similar, their angles are equal to each other. When they have exactly the same shape, this angle and this angle will be equal, the top angle and the top angle will be equal, etc. To prove that two triangles are similar, all you have to do, though, is show that two angles of one are equal to two angles of the other. And since the total interior angles of a triangle always total to 180, you get that the third angles are equal for free. So once again, you do not have to show all three angles of one triangle are equal to all three angles of another in order to show they're similar. If you can show that two angles of one are equal to two angles of another, they're similar. Now, similar triangles have the same shape, but as you can see from the drawing, they don't generally have the same size. And sometimes it can be difficult to tell if two triangles are similar. For example, if I take that first triangle and I rotate that first triangle counterclockwise as shown here, then when I compare the big triangle to the small triangle, it's very difficult to tell if they're the same shape or not. And that's because the angles are no longer in the same corresponding position. Notice that in the small triangle, my double hatch is at the top, where in the big triangle, after rotating it, the double hatch angle is at the bottom left. We say that these two triangles are oriented differently, while the first two triangles are oriented the same. So when they have the same orientation, their angles will be in the same relative position. If the double hatch is up in this one, and this one is oriented the same as the one on the left, then the double hatch at the top here will be matched by a double hatch at the top here. Now let's label the triangles. We'll call the first one ABC, and we'll call the second one DEF. And if we were to label the third one is the same as the first one. And notice that in the first one, A is between the double and the triple. So if I'm naming the third one, I'd call that A. B is between the single and the double, so I'd call that B. And C is between the single hatch and the triple hatch, so between those I'd call this side C. When the two triangles are oriented the same, the sides in the same position are called corresponding sides. For example, in my first two drawings, the two triangles are oriented the same. So the corresponding sides here would be A and D because they're both on the left, E and B because they're both on the top, and C and F would be corresponding sides because they're both on the bottom. And in our rule it says, with similar triangles, corresponding sides are proportional. Proportional means that if you draw a ratio of corresponding sides, like A to D, then that is going to be exactly the same ratio as the ratio of any other two corresponding sides. So A to D would be the same ratio as B to E, so I could put an equal sign between them. And that would be the same ratio as C to F. Now you can't just arbitrarily splash these letters in. If I had put E over B, this first would not have been correct, even though E and B are corresponding sides. Because notice that in the ratio A to D, I took a big side A and put it over a small side D. So I have to maintain that discipline. If I'm going to write the ratio from B to E, I have to again take the big side and put it over the small side. If I'm going to do the ratio between F and C, I again have to put the big side over the small side. Now that's not to say I couldn't have set it up the other way. If I wanted my first ratio instead of A to D to be D to A, that would be fine. That's a small side to a big side. But as I write my other ratios, I have to keep that the same. So if I want the ratio between E and B, I still have to put the small side over the big side. And if I want the one between C and F, I still have to put the small side over the big side. So once you've established a big to small or a small to big, you have to keep that up as you write your ratios. Now with that kind of background, let's go ahead and take a look at some example problems to see how similar triangles can be used to find missing sides. So in example 1 it says find sides X and Y. Both are missing sides. Both are sides that we don't have a dimension for. But we do have dimensions for the other sides. And in particular, when you look at the 16 and the 24, those are corresponding sides because they're both the sides that are between the double hatch and the single hatch. So that would establish a ratio that I could use as a base. Remember, you need a known ratio of corresponding sides. So I'll put my big over my small, 24 over 16. Now suppose I'd like to find X. The corresponding side to X is not Y, so don't stick them in the same formula. X is on the right, Y is on the top. The corresponding side to X is the 9. Now in my original ratio I put big over small. The X is bigger than the 9, so again I put big over small. And there's my setup, and now I can solve for X. I set cross products equal. 24 times 9 is equal to 16 times X. To get X by itself, I divide both sides by 16. I notice that 16 is 8 times 2 and 24 is 8 times 3, so I cancel the 8s. That leaves me a 3 on top and a 2 on the bottom. So I end up with X is equal to 27 halves, which is the same as 13 and a half. You can leave it 27 halves or 13 and a half, makes no difference which. Now, if I want to go to find side Y, I can still use the established ratio of 16 to 24 or 24 to 16, either way I want to do it. But corresponding to side Y will be side 30. So let's say this time I decide to set up small to big. There's no particular reason to do that. That's just what I'm going to do. So I'm going to set up small to big here. So instead of writing 24 to 16, I write 16 to 24 is equal to, and now I want a ratio that has Y, so I can solve for Y. Well, the tops are Y and 30, so I put small y over big 30. And now set my cross products equal. And I get 24y is equal to 16 times 30. I divide both sides by 24, and again on the left of course they cancel. On the right I again observe that 24 is 8 times 3, 16 is 8 times 2, so if I cancel the 8's out I'm left with a 2 on the top and a 3 on the bottom. But this time I can cancel the 3 into the 30, so I cancel the 3 into the 30 and I get 10. So I end up with y is equal to 20 even. Let's go on now to the second example. The second example is the beginning of some examples which kind of get complicated. It's the case where you're dealing with two similar triangles, you're looking for a missing side, but the two triangles touch each other. In that case, I'm going to very strongly make a recommendation. Any time that you're doing a similar triangles problem and the two triangles touch each other, separate them and relabel them. Separate them and orient them the same. So let's say I'm going to pull the big triangle out of this picture and redraw it below the small triangle, separated from the small triangle. I want the square hatch to be on the lower left. So I draw the big triangle and I put the square hatch to the lower left, like so, and then the single hatch to the lower right, so it'll be the same as the small. Now I've got the two triangles oriented the same. Now I've got to label them. So where does the X go? Well, the X was across from the small single hatch. So I'll put the X across from the small single hatch. To get to the 30, I went X, square hatch, 30. So I go X, square hatch, 30. And now I've got my two triangles, the small one and the big one, oriented the same. Once they're oriented the same, it's very easy to see how to do my proportion. I set up X is to 8, big is to small, as 30 is to 12, big is to small. And I'm using my corresponding sides, left is to left as base is to base. I set my cross products equal. I get 12x is equal to 8 times 30. I divide both sides by 12, and I get some good canceling going on. 8 is 4 times 2, 12 is 4 times 3, so I'll cancel the 4's, and I'll have a 2 left on top and a 3 left on the bottom. And then again, 30 is 10 times 3, so I'll cancel the 3 on the bottom with the 3 and the 30, and that'll leave me a 10. So I get x is equal to 20. Moral to the story: if two similar triangles touch each other, separate them before starting the problem, reorient them so that they're separated and oriented the same, relabel the triangle that you separated out, and then write your proportion. It can be very confusing to try to write your proportion while the triangles are touching, and to see that even more clearly, let's look at a slightly more complicated example. Now in the next example, again, I have my two triangles touching. The big triangle is the triangle with top side 20 and right side 9. The smaller triangle has a top side I'm not aware of. I don't know exactly what that is. I know it's less than 20, and the right side is 7. So the one triangle is kind of contained within the other triangle. I know that they're similar because I've got single hatch marks on the lower. That means one angle of one is equal to one angle of the other. And they share this angle. This angle is in both triangles. So that's two angles of one equal to two angles of the other. And again, the secret to this problem is going to be to separate them. So the first thing I'm going to do is separate them. I'll draw the small triangle as well as I can draw it here on the left. And I'll do the bigger triangle on the right. And now I'll relabel the known sides. The right side of the big one was a 9. The right side of the small one was a 7. The base of the small one right here is a 12, but what is the base of the big one? Well, the base of the big one is this stretch right here from here to here. And it's 12 from here to here, plus another x from here to here. So this side is 12 plus x. It's not 12x, it's 12 plus x. Now notice that I now have enough that I can write a proportion, and I never even needed to use the 20. So just because a dimension is given in a picture doesn't mean you have to use it to solve the problem. I'm going to be able to solve this problem without using the 20. I set up my proportions. I'm going to do big 12 plus x is to small 12, that's bases to base, as right side big is to right side small. I set my cross products equal. On the left, I'll have 7 times 12 plus x. On the right, I'll have 12 times 9. 7 times 12 plus x is 84 plus 7x, and 12 times 9 is 108. I subtract 84 from both sides, and I get 7x is equal to 24. Let me just take that over here so I can finish off. 7x equals 24. I divide both sides by 7 to get x by itself, and I get x equals 24 sevenths. If you change that to a mixed number, that would be 3 3/7. So that's kind of an ugly answer. Don't think that your answers are also always going to come out beautiful. If you wanted to do your 24/7 on your calculator, you could. I'd give about a 3-digit answer to that. Let's go on to our last example now. It's an even more complicated case of two triangles touching each other. This time the orientations are really messed up, but it's still easy to orient them correctly. I know that since they're similar, and I know they're similar because you can see the single hatch here equal to the single hatch, the double hatch here equal to the double hatch. So two angles of one are equal to two angles of the other. So to separate and reorient, I'm simply going to draw the smaller triangle as well as I can below the big one. It looks something like that. I may not have it exactly right. I know that if they're going to be oriented the same, that has to be the double hatch and that has to be the single hatch. And so now I'm prepared to put my measurements on the smaller triangle. If I want to see where the 9 is, I do the following. Rotating clockwise, I could go single hatch, double hatch, 9. So I rotate clockwise and go single hatch, double hatch, 9, and that puts the 9 right there. And then if I wanted to locate where the 20 is, well, the 20 was across from the double hatch. So I'll just put the 20 across from the double hatch. Now I've got the small triangle oriented the same as the big triangle. And now I'm ready to write my proportion. I'll start off with a big is to small. I'll take the left side of the big triangle and do the ratio with the left side of the small triangle. That's 12 is to 9. But then what is the top of the big triangle? Well, the top goes all the way from here over to here. And from here to here, it's x, plus from here to here, it's another 20. So the top of the big triangle is x plus 20. The top of the small triangle is 20. And now I'm ready to solve for x. I set my cross products equal. I get 12 times 20 is equal to 9 times x plus 20. And notice it's 9 times the whole x plus 20. So that x plus 20 must go in a bracket. Now, there's two terms in the bracket, so I'll distribute that 9 twice. So I'll get 240 is equal to 9x plus 180. 9 times 20 being 180. I'll subtract 180 from both sides. I get 60 equals 9x. Finally, to get x by itself, I'll divide both sides by 9. The 9's cancel. And I get x equals 60 over 9. That's 3 times 20, 60, over 3 times 3, 9, and the 3's cancel. So I end up with x is equal to 20 thirds. And if you'd like that as a mixed number, that would say x would be equal to 6 2/3. And of course, you could also pop out the 20 over 3 on your calculator. You'd get 6.666. So if I kept about 3 digits, we would say approximately equal to 6.67. So when you have two normal similar triangles oriented the same, just do ratios of corresponding parts. Remember, if you go big as to small on one side, do the same on the other side. But if your two triangles are touching, always separate them and relabel them before you write your proportion, and that way you won't make any mistakes writing your proportion. That completes the podcast.